The Bohr atom is a strange and wonderful concept. It's quite different from that model of Rutherford. In the Rutherford simple planetary model, you have electrons orbiting a massive nucleus, just like planets around the sun. But in the Bohr model, electrons adopt very specific discrete energy levels. Electrons can remain stably in their orbits, or they can change energy levels one to another. If an electron drops down from an upper energy level to a lower one, it emits a photon. If a photon is absorbed by an atom, the electron jumps up to a higher excited state. The Bohr atom thus models many of the distinctive properties of interactions of light and matter that we see every day. But we still have yet to come to terms with the different kinds of atoms. The great principle of this lecture is that all chemical elements are systematized in the periodic table of the elements. The periodic table is the chemist's playground. This icon of science, it's found on science classroom walls by the millions all over the country, all around the world. It's one of the most powerful conceptual tools in all of science. Yet it didn't spring forth all at once. It wasn't fully formed from one mind. This table represents countless centuries of collective work. That work continues today. My three objectives in this lecture, this is the 20th lecture of our series, are first to define the concept of the chemical element. I'm then going to review how Dmitri Mendeleev systematized all the known elements to produce his great periodic table. And finally, we're going to look at some of the consequences of this amazing synthesis of the periodic properties of the elements. Let's begin by looking at the nature of chemical elements themselves. Long before the existence of atoms had been proven, that wasn't until the 20th century after all, there still were chemical researchers all over the world who were looking to find useful compounds. And some of these substances that they found seemed to be more fundamental than others. These, quote, elements could not be broken down into other substances by any normal physical means, by any normal chemical means. Water, for example. You can take water and you can decompose it with an electric current, and it breaks down to two gases, hydrogen and oxygen. But no matter what you do, you don't seem to be able to break down hydrogen and oxygen to simpler compounds. They seem to be more fundamental. They are chemical elements. This identification of chemical elements has a long, long history. It was often characterized by slow progress, punctuated by very rapid bursts of discoveries of whole bunches of new elements as new technologies came along. And so we're going to see in this lecture the importance of developing new ways of studying the natural world. Ancient cultures knew of at least 10 different chemical elements. Most of these were found in their native state. Most of them were found as metals. We have the precious metals. That's copper, silver, and gold. They're common enough to be noticed. They're hard enough to be useful. They're rare enough to be valued. You have the precious metal platinum as well. Interestingly, platinum was not recognized in Europe or in Asia, but it was used by pre-Columbian peoples in the New World, partly because you could find platinum nuggets in the stream beds of parts of South America. Other metals are also found rarely as native elements. Under unusual circumstances, you have iron found as meteorites. You can find small quantities of lead, small amounts of mercury in certain types of places, and so those also occur uncombined in nature. Those are also naturally occurring elements. These metals, along with tin and antimony, could be produced in a fire from just common ores. Indeed, it may have been discovered by accident, some of these elements. An ore just drops into a fire and a little bit of this metal, antimony or tin, might have come out in that way. You also have non-metallic elements that occur in nature. Carbon comes from charcoal, and also sulfur from volcanoes. You find beautiful yellow sulfur crystals near the mouths of some volcanoes. All these elements, by the way, are still mined in large quantities today. Then we come to the 12th through the 16th century, the period of alchemy, where various scholars learned to separate a few other elements by using intense fires. The new elements discovered during this period include arsenic and zinc, bismuth, and phosphorus. Between 1735 and 1805, chemists devised new techniques to purify and characterize more than 24 new elements. This research went hand in hand with advances in mineralogy. Many of the new elements were discovered by studying minerals through wet chemical analysis, where you dissolved and broke apart the minerals, or by blowpipe analysis, where you used an intense hot flame to melt and fuse various parts of the minerals, and once in a while a new element would come to light in that way. The important elements nickel, cobalt, magnesium, chromium, molybdenum, tungsten, uranium, they were all discovered during this period. Also during this period was the first isolation of gaseous elements, hydrogen, nitrogen, and oxygen. All of them were isolated between 1772 and 1774. The most dramatic of these discoveries was made by the British chemist Joseph Priestley, who lived from 1733 to 1804. It was in the year 1774 that Priestley subjected mercury oxide, a common mineral that you can collect off the surface of the earth, that's HGO, or mercury oxide. He subjected that to a temperature of about 450 degrees centigrade, and that resulted in a puddle of mercury forming at the bottom of his vial and releasing a gas, which turned out to be oxygen. He collected that gas, oxygen, in his containers, and he found that this is the gas that's essential for all burning processes. Indeed, he wrote, quote, "What surprised me more than I can well express was that a candle burned in this air with a remarkably brilliant flame." So he had discovered a pure source of oxygen. The battery provided an important new technique called electrolysis. And by this technique of electrolysis, new elements can be produced and isolated. Recall that the battery was invented by Luigi Galvani, who placed an alternating sequence of plates, for example, zinc, silver, in an acid bath to get an electric potential. Electrolysis works like this. You dissolve a chemical compound in an acid bath, and then you subject that acid bath to the electrical current. You have a positive electrode and a negative electrode created by these alternating plates of metal. Metals are often deposited on the negative side, on the anode side, while nonmetals concentrate on the cathode, the positive side of this acid bath. In this way, you can isolate new elements, one going to each of the two electrodes in some cases. This was beginning in 1797 that the battery was used to discover new elements. The British chemist Sir Humphrey Davy, about which I told you about before, he was that great lecturer in London. He used increasingly powerful batteries to separate potassium and sodium, boron, calcium, barium, cadmium, all very important elements that were separated and isolated for the first time by Davy using his battery. Today, electrolysis is the primary means for commercial production of many, many elements, including aluminum. Virtually all aluminum is produced in this way. Order was given to the wide and the growing range of chemical elements by the Russian chemist Dmitry Mendeleev. He lived from 1834 to 1907. He was born in Siberia, and he was the youngest of 14 children. His father was a teacher of Russian literature, and he received an excellent education from a very early age. He eventually attended university in St. Petersburg, and he studied chemistry. Many of his earliest publications relate to the chemical analysis of minerals and also of petroleum, materials from the earth. That was the raw material for chemists in this period, the unusual minerals, the petroleum, all the different substances you could get out of the ground. It was this work, along with his interest in teaching chemistry, that led him to search for systematics in the patterns and the properties of the different chemical elements. Mendeleev knew of 63 different chemical elements. This was his data. This was the raw material of his study. And that's when he began working on his famous table in the 1860s. Turns out that chemical elements have a whole number of measurable properties, and this provides the basis for grouping the elements in various rows and columns and various patterns and so forth. You have relative weights. You can measure the relative weights by observing ratios of the weights when compounds are decomposed. When water is decomposed by electricity, for example, it produces 2 parts hydrogen to 1 part oxygen gas by volume, 1 to 8 by weight. So you have all these different ratios, weights and volumes and so forth. By measuring the decomposition of many different compounds, the relative weights of many different elements can be determined. If hydrogen has weight 1, for example, Mendeleev found that sodium has weight 23, calcium is 40, barium is 137, for example. All the elements then can be arranged in sequence according to increasing weight. elements also displayed other systematic properties. During electrolysis, for example, a mineral or other compound is dissolved in acid. The two electrodes, of course, separate out these elements. And what you found is that a few elements, including oxygen and chlorine and bromine, always went to the positive electrode. These gases can be collected, they can bubble up through the acid, and you can collect them there. Metals are always deposited at that negative electrode, and so you can collect the metals and determine their properties. So, for example, if you take silver chloride and you dissolve it in an acid, the chlorine gas comes bubbling up off the positive side. The metal, the silver metal, is plated onto the negative anode. In fact, this is the principle for silver plating and other kinds of metal plating by electrical methods, which are called electroplating in a general sense. You do it just using a battery and dissolved metals in the solution. Turns out that the amount of voltage required to initiate this process is also one of the periodic properties. As you go across certain sets of elements, you see there's a systematic pattern. You need more voltage for some elements than others. Long before Mendeleev's work, chemists had recognized that some groups of elements show striking similarities, striking patterns. This is true for their physical appearance, for their chemical properties, and other sorts of behavior. Furthermore, for each of these groups of related elements, the physical and chemical properties seem to somehow change systematically with their weight. And let me give you a few examples of these periodic properties. The elements lithium, sodium, potassium, and rubidium, for example, are all soft, silvery metals. They're called the alkali metals. These elements all react violently with halogens, an element like chlorine, and you get a 1-to-1 ratio of sodium to chlorine or potassium to chlorine or rubidium to chlorine. They're all soluble in water. In fact, they all react somewhat violently with water. They also all burn rapidly to form 2-to-1 compounds with oxygen. For example, sodium-2 oxygen or rubidium-2 oxygen. It turns out that lithium is the least reactive. That's the lightest one as well. Rubidium is the heaviest, and it's the most reactive. Despite their similarities, the relative weights of these four compounds, lithium to sodium to potassium to rubidium, are a rather odd ratio. It's 7 to 23 to 39 to 85. It seems rather arbitrary, and so you don't really know what to make of that. Let's look at another group of elements, what are called the alkaline earth metals. These include beryllium and magnesium, calcium, and barium. They form 1 to 2 compounds with chlorine, such as calcium 2 chlorides, or a 1-to-1 compound with oxygen, such as calcium 1, oxygen 1. That's called lime, by the way. The relative weights of these four silvery metals is 9 to 24 to 40 to 88. Once again, it's an odd sequence of numbers, but think about those numbers, 9, 24, 40, 88 to 7, 23, 39, 85. There seems to be some sort of similarity. It's not an identical pattern, but there certainly is something very close there. So Mendeleev would have noticed that sort of thing as well. And then we have another group called the halogens, chlorine, bromine, iodine. They're all highly reactive nonmetals. They form 1-to-1 compounds with hydrogen, 1-to-1 compounds with the alkali metals, 2-to-1 compounds with the alkaline earths. They're all gases or liquids. Their relative weights are 35, 80, 126. And those numbers 35, 80 are very similar to the 39, 85 ratio of potassium and rubidium in the alkali metals. So once again, there seems to be maybe there's some mathematical relationship there, but it's hard to know whether that's significant or not. Still, other elements, such as hydrogen and carbon and sulfur, were more difficult to group in any systematic way. There didn't seem to be any other elements that were exactly like those. So Mendeleev had to be very puzzled when he saw this complete array of elements and tried to systematize them. So I guess part of his success was his ability to focus on the most obvious patterns and then not worry too much about anomalies that seem to creep in. This is a kind of intuitive step in science. It's true of virtually every major scientific discovery. You have to know what details to ignore when you make your synthesis. Galileo ignored the significant effects of wind resistance when he was studying rolling balls and curving objects. He said, let's see if we can eliminate wind resistance as a problem. Newton had to see very simple patterns in complex motion. He had to ignore all the different kinds of varying accelerations and just say there's uniform motion and there's acceleration and ignore the complexities. The pioneers of thermodynamics had to zero in on similarities amongst many inherently different kinds of energy: kinetic energy, heat, gravitational energy. You had to somehow be able to clear your mind of all the variations that you see in the natural world and focus it on fundamental similarities, and that's not an easy thing to do. Mendeleev forced the most unambiguous groups of similar elements into vertical columns. He said, I'm going to put lithium, sodium, potassium, rubidium into one column. Beryllium, magnesium, calcium, barium is in another column. Chlorine, bromine, iodine, that's going to be in a third column, and so forth. He also arranged his elements left to right, and top to bottom by increasing weights. Thus, sodium was next to magnesium, potassium was next to calcium, and so forth. So he had a side-to-side arrangement, a top-to-bottom arrangement based on weight. He also left spaces for elements that appeared to be missing. For example, his table left room for unknown elements in positions 2, 10, and 18. There were also obvious gaps at element 21 and element 32, elements which had not been described and yet would appear to be present if the table was complete. Scientists readily accepted the concept of the periodic table, not only because it systematized so much of what was known, but because it made very specific testable predictions about what was not known. One apparently missing element lay on the fourth row between calcium and titanium. That's scandium, element 21. It was discovered in 1876, just as Mendeleev predicted. Another gap seemed to occur in the column headed by carbon. The element below that is silicon, and above tin there was a blank. Germanium, element 32, was discovered in 1886, and it filled that blank. New elements continued to fill out and expand the periodic table. For more than a decade, between 1863 and 1875, there were no new elements discovered. The old technique of electrolysis had been pushed to the limit. Blowpipe analysis was no longer effective to find new elements. And it was the development of flame spectroscopy, which I told you about in the last lecture, by which elements could be identified by their distinctive bright line spectrum when they were heated up to an incandescent glow. This triggered another wave of element discoveries in the mid-1870s through the 1890s. You could identify each new element by its unique fingerprint when it glowed. Recall that every element has its own distinctive set of electron energy levels. Thus, each element, when it's heated to high temperature, has its own unique set of wavelengths that are emitted as electrons are heated up and drop back down. And you can use those distinctive line spectra to distinguish new elements. More than 24 rare elements were discovered in this way in this period in the late 19th century. Many of the rare earth elements, the so-called rare earth elements, these are elements number 57 through 71. They were all discovered at this time. These heavy elements are chemically so similar that they always occur lumped together in minerals in the natural world. They all have very similar chemical properties, but you can distinguish them and isolate them using flame photometry. Many of the, between 1895 and 1898, we also had the discovery of many of the inert gases. And these discoveries were made by the Scottish chemist William Ramsay, who lived from 1852 to 1916. He used spectroscopy to identify 5 of these inert gases. Sometimes they're called noble gases. These are elements that are so unreactive that they don't bind to anything. They occur only as isolated gas atoms in nature. Mendeleev's table predicted you'd have element 2 and 10 and 18. These are what we now know as helium, neon, and argon. These previously unseparated elements added a whole new column to the periodic table, and that column was also amplified with krypton and xenon, which are part of these groups. Ramsay, by the way, received the Nobel Prize and many, many other honors for this work in adding a whole new column to Mendeleev's table. Mendeleev's periodic table was incomplete in other ways as well. He had to include the element fluorine, which was well known to be a major component in many common minerals, especially in calcium fluoride, the mineral fluorite. Yet no one had been able to isolate fluorine. And this effort became a major challenge in the late 19th century, the effort to isolate the element fluorine, to show what the properties of fluorine might be. Mendeleev's table provided some useful hints. Fluorine was at the top of the column containing chlorine, bromine, and iodine. These are all extremely reactive nonmetals, and they could be produced by electrolysis of sodium or calcium compounds. The periodic properties suggest that fluorine would require an extremely high voltage. It would be extremely reactive, a very, very dangerous substance. And so it was that early attempts to isolate fluorine with electric current were disastrous. They caused injury, they caused death to many chemists. Strong batteries could indeed separate fluorine from calcium. For example, you take calcium fluorite, the fluorite mineral, and you can separate fluorine. But the gas turns out to be so reactive that it attacks and destroys tissues almost immediately. It's one of the most dangerous chemical substances known. Fluorine, it turns out, is the strongest electron-attracting element that exists. So it steals electrons. It disrupts the bonds of other chemical substances. Fluorine can be released, but it immediately recombines with its surroundings. That includes skin and the lungs of chemists who tried to study it. Humphrey Davy in England was one person who suffered this way. The rival French team of Joseph Gay-Lussac and Louis Thénard tried and failed, only to experience debilitating eye irritation, respiratory inflammation. There's a story of the Irish brothers George and Thomas Knox, who suffered horribly when they were exposed to hydrofluoric acid. Thomas almost died. George spent 3 years recovering his health. George Gore of London was another chemist. He managed to isolate a small quantity of fluorine, but it exploded and destroyed his laboratory. And they were apparently the lucky ones. You had Jerome Nichols of France and Pauline Louet of Belgium. They died horribly in their laboratory. They were asphyxiated. Their lungs and skin were blistered by this corrosive gas. Can you imagine the horror of producing this gas and then dying as a result of your chemical experiments? So the isolation of fluorine remained a great, great challenge in the late 19th century. In 1886, French chemist Henri Moissan successfully isolated the element after almost 3 years of effort. He passed a strong electric current through a solution of fluorine salts, just as his predecessors have done, and sure enough, the fluorine gas bubbled up. But the thing he did differently is he built his entire apparatus out of fluorite, which is probably the only substance that would contain the fluorine gas, because it already was fully saturated with fluorine. He won the Nobel Prize for this work. And even so, even though he was able to do this, he said that it probably took 10 years off his life, this successful effort to isolate fluorine. It was a great chemical challenge, but the people who did it really paid a price. There were other chemical discoveries. There were other discoveries of new elements I should tell you about. One of the most important was made by the Polish chemist Marie Curie, who was assisted by her husband Pierre. They isolated the first radioactive elements, polonium and radium, in 1898. These elements spontaneously emit high-energy radiation. They transform into other elements, as we're going to see in Lecture 27. The whole history of radioactive elements is a fascinating one, and I will tell you more about that in that later lecture. For the final part of this lecture, let's look at some of the implications of the periodic table. The development of the Bohr atom led to a deeper understanding of why the periodic table works. The periodic table, you see, systematizes two key properties of the elements: their weight and their chemical properties. The weight, or the mass, of elements increases from left to right, top to bottom of the periodic table. Mass results primarily from particles in the atom's nucleus. This is what Rutherford found, that it's the nucleus that carries the mass of the atom. Heavier elements generally have more protons in the nucleus, therefore. Rutherford showed that since most of the mass is in that positively charged nucleus, then you could characterize mass and the number of protons as sort of a one-to-one thing. Increasing weight corresponds to increasing the size of that nucleus. The lightest element is hydrogen. It has one positive charge and thus one proton in the nucleus. Successive elements have additional positive charges. So helium is element 2, it has 2 protons. Lithium is element 3, it has 3 protons, and so forth. More and more massive nuclei, and each different atom corresponds to a different number of positive charges in the nucleus. This is the element's atomic number. It represents both its position in the periodic table and the number of positive charges. So the atomic number defines the element name as well as its chemical properties. Hydrogen is a shorthand name for the element with 1 proton. Gold is a shorthand name for the element with 79 protons. For an atom to be electrically neutral, it has to have the same number of negatively charged electrons in orbit around the positive nucleus. Any difference in the number of protons, which is fixed, and number of electrons, which can be added or stripped away, makes an ion. If you have more electrons than protons in the nucleus, you have a negative ion. If you have fewer electrons, if some electrons have been stripped away, you then have more positive charges, and it's a positive ion. The chemical behavior of an element is a reflection of the interaction between two or more atoms. Since an atom is almost entirely empty space, this means that it's the arrangement of the electrons that are circling on the outside, sort of the outer guard, if you will, that specifically the outermost electrons of that arrangement, that determines the chemical behavior. The periodic properties of the chemical elements then suggest that similar chemical properties are the result of atoms that have similar arrangements of outer electrons. Remember that the elements are arranged in columns according to similar properties. That's why, from a chemical point of view, lithium, sodium, potassium, rubidium have similar chemical properties because they have a similar electron arrangement. We now know that electrons combine in shells around the nucleus. Each row of the periodic table corresponds to one of these electron shells. So we can move from left to right in the table. Let's look at the first row. You have hydrogen with 1 electron and 1 proton, helium with 2 electrons and 2 protons, and that's the first row, completely filled. So apparently the innermost shell of electrons can hold up to 2 electrons. Similarly, the second row, if you go across that, it has 8 different elements, and so the second shell of electrons apparently can hold up to 8 electrons. The third through the sixth rows have 8, then 18, then 18, then 32 more electrons successively. So you keep adding and adding and adding electrons as you go farther and farther down and from left to right in that periodic table. The key to understanding how atoms combine is that there are certain magic numbers of electrons. And these magic numbers of electrons appear to be more stable than any other numbers. By far the most stable electron configurations are atoms that have 2, or 10, or 18, or 36, or 54, or 86 electrons. Those are the magic numbers. The periodic table reflects this fact. The first 5 rows of the table end in inert gases. Remember, inert gases are elements that exist as isolated atoms. They don't bond to anything. They're particularly stable. And those are elements 2, 10, 18, 36, 54, and 86, the magic numbers. Each of these elements has a completely filled outer shell of electrons. These inert gases don't need to bond to anything. All the elements in the first row have a single, in the first column, have a single electron in their outer shell. These atoms need to lose an electron in order to get a filled outer shell. So they bond in similar ways, that first column. All the elements in the next to the last column have electron shells that are 1 electron short of being full. That's like the chlorine, the fluorine, and so forth. So all of those elements need to get 1 more electron to fill their outer shell. As we're going to see, these systematic trends played the key role in the formation of chemical bonds. Let me summarize Lecture 20. First, we saw the chemical elements or substances that can't be broken down into simpler substances by any ordinary chemical or physical means. Throughout the 18th and the 19th century, chemists isolated more and more of these new chemical elements, in addition to the dozen or so elements that had been known to the ancients. In 1863, Dmitri Mendeleev systematized the 63 chemical elements that he knew about into a periodic table. That organized all the known elements into columns according to their chemical behavior, in rows according to their weights. The table had clear gaps that made predictions, and many of those predictions were found to be filled when new elements predicted by Mendeleev were then discovered subsequently. Finally, we saw that the structure of the periodic table reflects the arrangements of electrons in atoms. In particular, atoms that have 2 or 10 or 18 electrons and so forth have completely filled electron shells and thus are particularly stable. Much of chemistry can be understood as a game in which every atom or group of atoms adopts a strategy to achieve one of these magic numbers of electrons, 2 or 10 or 18 and so forth. These strategies are called chemical bonding. and that's the subject of the next lecture.